everybody. Today we are going to present our mechanical engineering design project, which is the design and manufacturing of a low-cost autonomous robot vacuum cleaner. Our main aim was to design a low-cost autonomous robot cleaner with 3D printed materials. We used fan blower and side brushes to ensure that robot efficiently cleans any surface area. In addition, with the help of low-cost ultrasonic and infrared sensors, we aim to build a robot cleaner with room mapping feature. We designed every part of the robot cleaner from scratch, except the electronic equipment. As you can see in the left side, our exterior design was made to easily attach all the equipment. After the CAD drawings, the challenging 3D printing stage have arrived. Since our exterior parts were big, we could not print the external parts as a whole. To reduce printing errors and time spent on manufacturing, we divided our large parts before printing. On the inside of the robot cleaner, we also designed and printed the dustbin and fan connector to successfully transfer the airflow from the bottom of the robot to the top. For hygiene purposes, we also included a HEPA filter that cleanses the air flowing through the outlet. In these pictures, you can see all the materials we used for the robot. As discussed, fan connector and the dustbin was placed on the middle of the design. We placed the fan under the connector. In the right and left sides, we placed two continuous servo motors and connected them to our wheels. To support the balance and movement of the robot, we also placed a ball roller on the back. We placed our LiPo battery on the back of the robot to arrange our center of gravity. We used 4 ultrasonic sensors placed on two on both front and 2 on sides. We also include 2 infrared sensors placed downwards to detect any sudden height change on the bottom. Finally, on the front side, we placed 2 side brushes and 2 additional servo motors for better sweeping and cleaning.
In mathematical models, we have calculated different equations to see that whether the hardware that we bought was suitable for our model. The first thing we have calculated was the battery life calculation. After summing up all of our consumptions and dividing it to our battery capacity, we have estimated that our robot is going to be good for 1.5 hours with our LiPo battery. Next, we have calculated our motor power calculations. By using the data that we have gotten from the servo motors data sheet, we have calculated that at the maximum volts, our motors are going to have 3.4 watts of power. And for this, we have used the equations on the left-hand side. And then we have calculated some wheel-related calculations for our coding as well. One of the first things that we have calculated was the driving force by using the applied torque that we have found in the previous slide. We have found that our driving force is going to be around 14 newtons. And then we have calculated the movement of the robot after one full rotation of our servo motors, which was again needed in coding. And we have calculated that that was around 0.2 meters. And then we have calculated turn angle needed for our servos to turn right and left. And then we have, for this, we have calculated this inequality. And then we have calculated our angle needs to be 257 degrees. But since our servo motors were not the same, a modified version of this angle used is in our code. And lastly, we have modeled our fan in ANSYS with dustbin to check whether our dustbin is able to handle the airflow without getting damaged. You can see the fan and dustbin's cross-section in ANSYS modeled in 2D. You can see the maximum pressures and maximum velocities modeled in contour in ANSYS. You can also see the animation in here. Here, it looks like the particles are leaving the dustbin, but since we actually have HEPA filters in here, the dust in the air is actually filtered in here and stays in the dustbin.
So we have coded the robot to first map the room, then start sweeping. In the left video, it can be clearly seen that the fan takes most of the dust into the dustbin from the ground. Other 2 videos shows the control mechanisms that we have coded to prevent the robot from falling down from higher ground via IR sensors. The next video shows the room mapping stage. When the robot is put down to the ground, it moves directly to the wall it faces. After reaching to the wall, it rotates to the left to start the mapping stage. While mapping the robot always follows the right-hand side wall. When the robot encounters a corner, it rotates to the side in according to the flow of the right-hand side wall. After reaching to the starting point, the map generated can be accessed via web browser. The Wi-Fi module of ESP32 allows us to communicate with the devices that are connected to the same Wi-Fi. The expected and real outcomes can be seen side by side here. The difference is mainly caused by the errors in ultrasonic sensors and servo motors. Even though the servo motors are the same model, we have encountered with different turn rate problems which cause robot to shift sides. With ultrasonic sensors, we weren't able to gather correct data all the time, which caused robot to perform unwanted actions and results in correct map. Despite all the obstacles, we were able to successfully design and build a low-budget robot vacuum cleaner as we aimed. To lower the budget, we have used 3D print for most of the structure to improve our project. In the future, visual-based mapping can be added by using smartphone camera. The precise location tracking, such as extended Kalman filter, can be used to improve the AI. And the design of the project can be optimized since we have trouble with large number of the cable usage. We thank everyone that helped us. Thank you for listening.